All right, welcome back to lesson 2 of our Algebra 2 Rewind for our pre-calculus course. Today's topic is algebraic expressions and everything that encapsulates that topic. We're going to spend quite a bit of time exploring polynomials and something called the area model. You might be well versed with it, you might not. That's okay. We're going to delve into that a little deeper later on in this video. Today's learning objective includes we are learning to apply the area model to multiply two sums or two differences, so I can explain orally and in writing how the numbers and signs of the factors relate to the numbers in the product. I'll know I've got it when given quadratic equations. I can find the solutions and explain orally and in writing why the solutions make the equation true. All right, first and foremost, what is a polynomial? A polynomial in the variable x is an expression of the form a sub n times x to the n plus a to or a sub not to the n minus 1 x 1. There we go. Okay, so basically what is happening, I'm going to type out a decent amount of algebraic notation, is a polynomial is an expression that consists of an indefinite amount of terms, with obviously each term having a variable associated with it and a sub 0 being defined as a constant value. If the first term here, a sub n, does not equal 0, because if it does equal 0, then 0 times that variable will just be 0, so it wouldn't necessarily exist. We would define the polynomial to have degree n, and the degree of a polynomial is the highest exponent within the expression. You might recall from Algebra 2 that the degree has a considerable effect graphically on the behavior of the function. We're going to have obviously a much more in-depth conversation, not in this chapter, but later on regarding curve sketching various functions to different degrees. In this instance, we have a monomial. Monomial is, I would say, a cousin of a polynomial. A polynomial, remember, has many terms. A monomial, mono meaning one, would have one term. So we wouldn't say that this expression here, a sub k, x to the k, is a polynomial, because polynomial means many, and this has one term. So it's definitively a monomial. But each of these monomials, right, if we're able to tease out the individual aspects of a polynomial, we refer to them as the terms of the polynomial, right? Not the thingies, not the, you know what I'm talking about. In terms of algebraic manipulation, we add and subtract polynomials by using properties of real numbers. More or less works the same way it did when you were adding 2 plus 3 and subtracting 7 minus 4. Okay. The idea is to combine like terms. They're terms for the same variables raised to the same powers using the distributive property. You might be sitting there saying distributive property, but it's this idea when you're combining like terms that you're only adding the coefficients and you're leaving the variable component. So technically you're factoring out the variable component and just summing and subtracting the coefficients. When subtracting polynomials, remember that if a minus sign precedes an expression in the parentheses, then the sign of every term within the parentheses changed brutish. Right, we're going to distribute that negative value, whether it be, well, it's a minus sign, so we're assuming here it's going to be a minus 1, right? So it'll be -1 times whatever's inside the parentheses. So very quick, after you get that jotted into your activity, explain how to find the product of polynomials or other algebraic expressions. What do you know, or what can you recall from your time in Algebra 1 and Geometry and Algebra 2 regarding multiplying polynomial expressions, because here we are where we finally arrived at the area model. So in Days of Future Past, yes, I'm an X-Men Marvel junkie, your teacher might have shown you a technique known as FOIL. They might have shown you a technique known as double distribution. They might have shown you a technique known as the butterfly method. Uh, Insert yet another mnemonic device to help you remember. However, I'm going to take it back to the conceptual base. All of those techniques are very valid and applicable because they allow you to be more efficient. However, what is happening here when we have these algebraic expressions? Right? The reason why we use area is because area is the first iteration of multiplication applied to a real world scenario. Okay? It applies to rectangles and squares and other figures, but rectangular most importantly, of different lengths and widths. Okay? So let's assume that this rectangle here has a length of, or a width, we could say, of x minus 5. All right, let me write this as well. So I will draw a nice, I said a nice and I lied. There we go. I think I'm not too bad. Right, so this side of our rectangle has a length of x minus 5. That's our width. And it could be the length. It doesn't really matter, right? Because multiplication is commutative. It doesn't matter the order in which you multiply, right? So let's say that the length is 1 of 3x plus 7. Now bear with me. That's cool. Right, so in this instance, okay, here's our rectangle in our maroon, okay? It's subdivided into basically 2 rows, 2 columns, and it becomes nothing more than a multiplication table. In this box, we're going to be multiplying 3x times x. You don't have to demonstrate all of this work in your but I'm doing it for video purposes. In this section here, we'll have row 1, column 2, so 7 times x, which is 7x. In this location here, column 1, row 2, we'll have negative 5 times 3x, which will yield a negative 15x. And last and most certainly not least, we'll have 5 times 7, which will yield a negative 35. Okay, and then obviously we're going to come to our text box. We're going to type in our math font. We'll have 3x to the second power plus 7x minus 15x minus 35. And make sure that you simplify and combine your like terms. So, oops, that I have a cube here. Sleeping. Minus 8x minus 35. Right, and like I said, if FOIL is the way you want to go, double distribution, you name any other animal that corresponds to multiplying algebraic expressions, you are more than welcome to utilize that. I just think that when we get to much more difficult topics, the area model reigns supreme. Just my 2 cents, but there you have it. If you've never seen it before, if you have seen it before, hopefully that provides a little bit of clarity. So please make your way through and try to determine what 2y minus 5 quantity squared expands and simplifies to. And this diagram here builds off this idea of the area model. Scroll a little bit. Here we are. Okay, as we can see, let me grab my pen. Right, we have this quantity here, a plus b, right, which is going to represent the entire length of both sides of I would say this is a square, right? Raised to the second power because we are multiplying this length by this length. Okay, so they're demonstrating, right, that once again the crosshairs or subsections of this, we can call it a rectangle since we have A and B and they're not, we can't assume that they're the same, right? But we would have A times A, which will yield to A squared, A times B, B times B, and B times A. So it's very much so a visual multiplication table. Um, and it's kind of also why I like the area model, because it not only demonstrates an algebraic process, but it connects it to a visual representation of what's actually happening when we are multiplying those terms together. So moving on. Oops. Factoring an expression means the opposite of multiplying. To factor a trinomial of this form, x squared plus bx plus c, we note that all of this algebraic gibberish. So what does it actually equate to? Oftentimes we have to rely on our intuition here with factoring. Okay, so this algebraic expression here, x plus r, x plus x, if we go to multiply using the area model, FOIL, whatever you may see fit, this is ultimately what the outcome is going to be. So we need to select numbers r and s such that r plus s, oops, equals b, right? And you might have heard this phrase before with your Algebra 1 or Algebra 2 teachers if they've berated you about factoring, right? But they say, you want to pick two numbers and multiply to c or add to b. All right, and we'll talk through that process a little bit more over the next couple of slides. But if multiplication is not your strong suit, that's okay. We have a nice little formulaic path, but there is no, I would say, shortcut to this. However, I'd like to note that many algebraic processes are formulaic. However, I do strongly discourage a memorization of those formulas. Okay? Factoring in the multiplication of algebraic expressions are nothing more than geometrical facts about length, area, and volume, as we see here. The figure to the left shows how the formula for the square of a binomial can be interpreted as a fact about areas of squares and rectangles. All right, there are multiple ways to factor expressions. Right, we have traditional factoring that would probably unfold here. Notice since you are in pre-cal, I've changed the coefficients for the leading coefficients to values that are not 1. So these will be much more difficult than you would anticipate, but an expression like this will most likely require the use of a GCF, a greatest common factor. I will assist you in walking through part A, but you'll be tasked with demonstrating your knowledge and how much you can recall for B, C, and D. So in part A, what makes it so much more difficult is the fact that we have this 6 here. Now, once again, I've told you it's going to rely mainly on your intuition and how quickly you can multiply these values. Now, there is a alternative I may offer. Something that your teacher from Algebra 1 might have offered you is something known as the AC method, which is good, but sometimes a little cumbersome. So what I strongly encourage you to do is you can take the leading coefficient, 6, multiply it by our constant, which is 3, We arrive at negative 18, right? We need to list the factors of 18 that will provide us with a sum of 7. As we can see, that is clearly 9 and 2. Right? 9 minus 2, because we want it to be a positive, would give us a positive 7. Let me erase. Beautiful. Okay, so how do I use this information to support me in what I would do next? So before we can factor, I'm going to rewrite my expression up here. Say 6x squared plus 9x minus 2x based on the factors I've selected minus 3. All right. This brings us to a conundrum because we're going to employ or have to employ factoring by grouping, which is something we'll discuss later in this video. But in this instance, we would want to rearrange our terms and factor our expressions in this manner. Because what this allows me to do now, I can factor out a 2x, arrive with, what is this, 3x minus 1. And then on the flip side, I can factor out a 3. So I have plus 3. And then I'll be left with a 3x minus 1. And notice how I have the identical expression in both my first term, right, 3x minus 1, plus 3 times 3x minus 1. So I can further break down this expression to 3x minus 1 times 2x plus 3. Okay. Now that is a long route, very tedious, however you arrive there. You could jump from 6x squared plus 7x minus 3 and just rewrite the expression to this final factored form. But it requires you to really hone in on your intuition and your ability to recall your numerical facts quickly. So don't overwhelm yourself. Slow and steady will win the race. I'd like for you, after you've completed the last 3 practice problems, to take a moment and explain how the figure here verifies this formula. Notice you can go back 2 slides, so I went back 3, okay, and take a look at what's happening. You might want to relabel this second diagram, which is missing a critical component, hence this idea of subtraction. Okay, what side represents a plus b, what side represents a minus b, and share your answer with the class. That will jumpstart our conversation for tomorrow. So as I had just mentioned, right, in the previous 2 slides, we had to implement a factoring technique known as grouping. And that's going to happen exclusively when you have polynomials that have 4 or more terms. Okay. Usually they don't have an odd number of terms because that makes things pretty wonky. But as long as you have an even number of terms, typically 4 or something like 8, you will be able to factor by grouping. So since I've demonstrated the technique earlier in this video, I'm going to leave these 2 practice problems for you. And that brings us to the conclusion of this video. We will reconvene tomorrow, where we will spend some time working through some additional practice and content and ensure that we have our factoring skills sharpened and refined. Great work, and I will see you tomorrow.